Hello everyone, I'm Akash. In today's video, we will solve another question on linear algebra from Maharashtra State 2024 exam. Question is, let A and B are similar matrices, then consider the following statements. Trace of A equals to trace of B, determinant of A equals to determinant of B, the characteristic polynomial of A is equals to characteristic polynomial of B. Fourth statement is the minimal polynomial of A is equals to the minimal polynomial of B. Then these are the options. All the statements are true. Option B is none of the statements are true. Option C is only 1, 2 and 3rd are true. And option D is only 2nd, 3rd and 4th statements are true. So let's begin the solution. What is given? Given that A and B are similar matrices. And we know by definition of similar matrices, since A and B are similar, so there exists an invertible matrix say P such that B equals to P inverse AP. This is by definition of similar matrices. Since given that A and B are similar matrices, so there exists an invertible matrix P such that B equals to P inverse AP. Now, as this matrix is equals to this matrix, so their trace are also equal. So this implies trace of B is equals to trace of P inverse AP. Since these two matrices are equal, so their trace are also equal. Now, this can be written as trace of P inverse of AP, and this is nothing but, we know that for any two matrices A and B of same size, trace of AB is equals to trace of BA. So we use that property, trace of A times B is equals to trace of B times A. So this is nothing but trace of AP times P inverse. Okay. Since trace of AB is equals to trace of BA. Okay. Now, by associativity of product, this can be written as trace of A times P inverse. Okay. By associativity of this matrix product. And this is nothing but trace of A times I, since P times P inverse is identity matrix, and which is equals to trace of A. Thus, we have proved that trace of B is equals to trace of A. Thus, if A and B are similar matrices, then their trace are same. Okay. So, if A and B are similar matrices, then trace of A is equals to trace of B. So, statement 1 is true statement. Okay. Now, let's verify the statement 2, that is determinant of A equals to determinant of B is true or not. So let's begin. Now, since B equals to P inverse AP, therefore determinant of B is equals to determinant of P inverse AP. B equals to P inverse AP because A and B are similar matrices, so by definition B equals to P inverse AP by definition of similar matrices. Now, as these two matrices are same, so their determinant are also same. Okay. And by properties of determinant, we know that determinant of A1, A2 and up to so on An is equals to the determinant of A1 times determinant of A2 times up to so on determinant of An. Okay. So this can be written as determinant of P inverse times determinant of A times determinant of P. Okay. By properties of determinant. Okay. And also by properties of determinant, we have determinant of P inverse is nothing but 1 upon determinant of P, determinant of A times determinant of P, and this to get cancelled out. Okay, why? Because we know that as P inverse exists, so determinant of P is not equals to 0. So 1 upon determinant of P is well defined. So this determinant of P get cancelled with this determinant of P. Okay, and so what is remain is determinant of A. Thus we see that if A and B are similar matrices, then determinant of A is equals to determinant of B. So statement 2 is also a true statement. Okay. Now what is the statement third? The statement third is the characteristic polynomial of A is equals to the characteristic polynomial of B. Is it true? Yes, this is also a true statement. Okay, so let's quickly prove this statement. First, since A and B are similar matrices, so there exists an invertible matrix P such that B equals to P inverse AP. Okay, by definition of similar matrices. Now, recall what is the characteristic polynomial of a matrix B or a matrix A? The characteristic polynomial of a matrix B, if I denote that polynomial by CHB of lambda, okay, I have denoted the characteristic polynomial of a matrix B by CHB of lambda. It is equals to the determinant of lambda I minus B. Okay, the characteristic polynomial of a matrix B is equals to the determinant of lambda I minus B. Now, what is B? B is equals to P inverse AP. So this is equals to lambda I minus P inverse AP. And this is again, I can write this identity matrix as P inverse time P minus P inverse AP. Okay, I have written identity matrix as P inverse time P. Now, I can write this subtraction as P inverse times lambda times identity matrix minus A times P. Just I have taken common P and I have taken common P inverse and P from this subtraction. Okay. Now just use the properties of determinant. Which property? Determinant of A1 times A2 times and so on An is equals to determinant of A1 times determinant of A2 and so on determinant of An. So apply this property here. What we get? Determinant of P inverse time determinant of this lambda I minus A times determinant of P. And again, as seen earlier, as P is invertible matrix, so determinant of P is non-zero, and by properties of determinant of P inverse is nothing but 1 upon determinant of P. So this to get cancel out. Okay, so what is remain? Determinant of lambda I minus A, and which is nothing but the characteristic polynomial of a matrix A. Okay, thus we see that if A and B are similar matrices, then A and B have same characteristic polynomials. Okay, so the statement third is also true. What about 4? In fact, we can prove that the statement 4 is also a true statement. And by using these two statements, we can see that if A and B are similar matrices, then they have same eigenvalues. Okay, I will left this for you, proof of this for you, but I will provide the hints. Okay, to prove the statement 4, you have to use the definition of minimal polynomial of A, minimal polynomial of matrix. What is definition of minimal polynomial? The minimal polynomial of a matrix A is the least degree monic polynomial of which A is a root. Okay, the minimal polynomial of a matrix A is the least degree monic polynomial of which a is root. And the second thing that you have to use for proving this statement 4 is the fact that the minimal polynomial of a matrix A divides every polynomial of which A is root. For example, suppose g of A equals to 0. That is, g is a polynomial such that A is a root of g. Okay, g of A equals to 0 matrix. This is not a usual 0. This is a 0 matrix. Okay, so suppose g of A is equals to 0. That is, A is a root of the polynomial g. Then the result that I have said here is the minimal polynomial of A, say fa divides g. That is, the minimal polynomial of a matrix A divides every polynomial of which A is root. So you have to use this result and the definition of minimal polynomial to prove the statement 4. So this is also a true statement. If you have any difficulty in proving the statement 4, then please comment on this video. I will make separate short video on proof of this statement 4. Okay. So the all 4 statements are true. Hence the correct option is option A. Okay. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.